In this video, we're going to talk about something known as an outcome or probability. So an outcome is a possible result of any event or experiment. It's the possible result of an event or experiment. So for example, if I flip a coin, I have two possible outcomes. Either my coin can land on heads or my coin can land on tails. So it's just a possible result of something occurring. A sample space is a set of all possible outcomes. So for example, the sample space of rolling a six-sided number cube is, I can either roll a 1, a 2, a 3, a 4, a 5, or a 6. So this is considered sample space because these are the only outcomes that I can have if I roll a normal six-sided cube die. Now, probability is the likelihood of something happening. So the likelihood of an event occurring. So if I wanted to roll the number 3 on a die, then I would have 1 out of 6 chances because 3 only shows up one time on a dice, and there are 6 possible sides to that die. So I would have a probability of 1/6 of rolling a 3 on a dice. Or if I wanted an even number, there are 3 even numbers. So I would have 3 out of 6 chances, or 1/2. So probability can be written several different ways. You can write it as a fraction. So kind of like how I've been saying 1/2 or 3/5 or 1/6. You can write it as a fraction. You can also write it as a decimal. So if I wanted to know the probability of a coin landing on heads, it would be 0.5 or 1/2, or it could even be written as a percent. So 50% chance of landing on heads, 50% chance of landing on tails. And so when we're looking for the probability of a specific event happening, we would say the probability, or P, of A, or the probability of a specific event occurring. So for example, I've got 5 examples here on this page. So we're looking at finding the probability of each. So rolling a 2 on a 6-sided number die. So if I'm looking at a regular die, then the number 2 only occurs one time. And there are 6 sides to it. So my probability is 1/6. I could also write that as a decimal as 0.167, or simply 16.7%. Most of the time, you're going to see them written as either a fraction or as a percent. Not that that is exclusively how they're written, that's just the most common forms of writing a probability. So number 2, rolling rolling an even number on a 6-sided dice. So I have the number 2, 4, and 6 are all even numbers. So I have 3 possible outcomes, right, out of a sample space of 6. So my probability is 3/6. Or if we reduce that, simply 1/2. Number 3, flipping a fair coin and landing on heads. So if I flip a fair coin, landing on heads, there's only one head on a tail, or one head on a coin, and there are only 2 possibilities, heads or tails. So my probability is 1/2, or you could even write it as 50%, or you could write it as 0.50. Selecting a green marble from a bag containing 3 red marbles, 4 green marbles, and 5 blue marbles. So I am specifically looking for green marbles. So I have 4 possible green marbles. And now what I want is the total number of marbles in that bag. So 3 plus 4 is 7. 7 plus 5 is 12. So I have 4 out of 12. If I reduce that down, that is equal to 1/3, or I have a 1 in 3 chance of grabbing a green marble. So that means if I reached in that bag 3 different times, um, probability says, or statistically, I should be able to get a green marble 1 of the 3 times. You can also do probability using a Venn diagram. So Lila is spinning a spinner with sections numbered 1 to 8 and recording the results. Event A is spinning an odd number. Event B is spinning a number greater than 2. Show a Venn diagram. So we did learn in the last video that the Venn diagram is your universal set. So I'm going to let event A be my red circle, and event B is going to be my green circle. So A is spinning an odd number and B is a number greater than 2. So I'm going to start with event B just because it's easier. So for example, it is numbered 1 through 8. So 1 is not greater than 2. So 2 is also not greater than 2. It's equal to 2. So I have 3, which is both an odd number and greater than 2. The number 4, the number 5, the number 6, the number 7, and the number 8. Event A is spinning an odd number. Well, my odd number is 1, 3, 5, or 7. So now that I have a Venn diagram here that represents all the possible values, and then I have a random, not random, 2. 2 is neither odd nor is it greater than 2, so it is still in the box. Everything in the box is the universal set, but it does not fit in category A or category B. So if I'm looking at the probability of specific events occurring, then I can say that I have one value that is exclusive to set A. So if I wanted to roll the number 1, I have a 1 in 8 chance of rolling the number 1. If I wanted to know the probability of rolling a value greater than 2, but that is also odd, well, that is 3 numbers fall in their intersections out of an 8 section spinner, so I have a 3 out of 8 chance. If I wanted the probability of rolling a value greater than 2 but is not odd, that is the green circle, but only the numbers that are not in the intersection. So those are 3 out of 8. And if I wanted the probability of rolling a value that is neither odd nor greater than 2, well, that is just the number 2. So I have a 1 out of 8 probability. So let's take a look at something known as tree diagramming. So tree diagramming is a visual representation of all possible outcomes or combinations of something occurring. So a way to find the total number of outcomes of more than one event. So for example, Miguel is going to select an outfit from 2, that's important, 2 different t-shirts, tan and red, 2 different pairs of shorts, gray and khaki, and 3 pairs of socks, black, navy, and white. So we're going to draw a tree diagram representing all the possible outfits. So what we do is we start off with what was given first. He has to choose a shirt, then a pair of shorts, and then a pair of socks. So he has 2 options for his shirt. He can choose a tan shirt, or he can choose a red shirt. From there, he is going to make his second selection. So we have a second branch of our tree. So the first branch represents your first choice, the second branch represents your second choice, and the third branch represents your third choice. So if he was to select a tan shirt, he then has to choose between a gray set of shorts or a khaki set of shorts. Same thing with his red shirt. If he chose a red shirt, he then has to select gray shorts or khaki shorts. So once he has his shirt and his shorts, he then has to select his socks. Now his socks have 3 different options. So each set of shorts will contain 3 options. Either he can pick a tan shirt, gray shorts, and black socks, or navy socks or white socks. He can pick a tan shirt with khaki shorts and black socks, navy socks, or white socks. So you can see that the sock selection, each selection gets its own branch. It is the 3rd branch in the tree because it is the 3rd choice. So how many outcomes are there in the sample space? So there are the outcomes, the total number of outcomes are represented by the very last branch of possible combinations on your tree. So there were 3 options here, 3 options here, 3 options here, and 3 options here. And we can see 3 plus 3 plus 3 plus 3 gives us a grand total of 12 possible outcomes or 12 possible outfit combinations. What is the probability that Miguel will select a tan shirt, gray shorts, and black socks? So we're going to start with tan shirt. So he's here. He then selects gray shorts. He is here. And black socks. He is here. Well, that particular combination is only 1 out of 12 possible combinations. What is the probability that Miguel will select an outfit with a red shirt and gray shorts? So he has a red shirt, gray shorts, and that's the only information that we're given. So he can have that combination with black socks, navy socks, and white socks. So there are 3 possible combinations, or 1/4. What's the probability that Miguel will select an outfit with khaki shorts? So this time we're going to start with khaki shorts, so it doesn't matter what color the shirt is. Well, those khaki shorts result in 3 options apiece. So he has 3 possible outfits with the tan shirt, and he has 3 possible options with the red shirt, or 6 out of 12, or 1/2, or even 50%, or even 0.5, depending on how you would like to write your probability. So sometimes our trees can get very large, and we have something known as the fundamental counting principle. So the fundamental counting principle is another way to find the total number of outcomes of an event occurring, especially when those values can be very large. So a deli is doing an inventory of their sandwich ingredients. They have 6 different types of bread, 8 possible meat combinations, and 4 types of cheese. And they want to know, well, how many kinds of sandwiches can they make? Well, you could draw a tree, but the tree is going to get very large, and sometimes it can get very confusing and we lose stuff because the tree is very large. So what I like to do is kind of set myself up as if I was making the sandwich. So first I need to choose my bread, and then I need to choose my meat, and then I need to choose my cheese. Now, when you have multiple choices like that, you're going to multiply all your possibilities in order to come up with the absolute total possible outcomes. So if I wanted to start with my bread, I had 6 different options for bread. Then I had 8 different options for meat, and then I had 4 different options for cheese. So if I take each one of those and multiply them out to come up with the total possible combinations, I would take 6 times 8 times 4, and that gives me a great combination of 192 possible outcomes. And you can see 192, that is a very large number. So if we were trying to graph this using a tree diagram, it would get very large very quickly for the total number of outcomes.